All right, so yesterday we talked about, hang on, where did I put my notes? All right, so yesterday we talked about this idea that when we have different forces that are in our system, we sort of have to accommodate for them a little bit differently in the actual equation. And so in particular, we took a look at an extension of a previous problem that we had looked at. So we saw a previous problem where it was a free, undamped system, but now we are adding some damping factors to that system. And so what we find out here is that we have this 16-pound object. It stretches a spring by 8/9 of a foot by itself. So that gave us maybe some what we could think about like ways to help us find that spring constant, like how stretchy is that spring. The spring was initially displaced 6 inches upward from its equilibrium point and given an initial velocity of 1 foot per second downward. And we also talked about how the directionality of the motion and of the velocity definitely needed to be taken into account when we're looking at putting things into the equation. Now, where we left was that we had said, hey, here's this differential equation, and we were going to solve it using the characteristic equation. And we got these roots, and then we were sort of left with what is that general solution. But before we got to that point, we also said, what about this 2 lambda, like that beta over m? Did we ever find that? And so one thing to keep in mind is that this beta right here, all right, so like the idea that you have this damping force, if we bring it back to this idea of force equals a certain value, so force from this damping factor, is going to be, so there's sort of a similar situation where it's not a spring constant in the sense that it is talking about like how stretchy the spring is, but there's actually this idea that there is a damping coefficient. All right, so maybe we should be more specific here. Instead of just writing force, let's write damping force. And we can find that by saying that whatever the constant is, so it'll be like our K, and let's maybe use K hat, all right? So there's different ways to annotate like things that sort of stand for the same thing but are slightly different. So like a K and a K hat is one way of doing it. Alternatively, you could use an entirely different letter, like K and M, or K and some other number or letter that you hadn't used before. And all of those ways are fine. Okay, you'll sort of like realize what feels more natural to you as you move through different problems. And it doesn't really matter what you call it as long as it has not been used yet. And so this damping force is this damping coefficient, and we're going to multiply it by the velocity that this damping force makes happen. So instead of a force equals spring constant times distance, we have a damping force equals our damping coefficient times velocity. So we sort of have this equivalent expression. And when we plug in our damping force of 17, when we plug in this damping force of 17, we get 17 equals K hat times 2, or K hat equals 17 half. All right. Now this 17 halves, what that tells us is that actually tells us our lambda, okay? So it tells us our lambda. Now what we want to do here though is we're gonna go ahead and double that because in our equation, we have a 2 lambda, All right. So instead of 17 halves, we're going to have 17 as this coefficient. The other reason why we're sort of doubling things, and this is probably a more accurate description, is that when we started off, we had a m value of 1/2, right? We had an m value of 1/2. And so when we take our values, our beta, and we divide it by that 1/2, we're going to end up with twice as much as when we started. So 17 halves divided by 1/2 will give us the 17. Okay, and that's the same reason why here, instead of 18, we just have 18 divided by 1/2. Okay. And so that hopefully is a little bit more clear about where these numbers come from and what we might have as our general solution here. Okay. And so when we think about our general solution, we do want to make sure that we know very much like what is that lambda, what is our omega, so that we can plug those into the equation. And so if we take a look at this, we see that we have e to the negative 17t. All right, so that 17, actually that's 17 halves, right? That 17 halves tells us sort of how quickly things are going to stop moving based on this damping factor. Like how much slower is that motion going to get with respect to time? And then on the inside, we can go ahead and plug in all of these values. So C1 e to the, this is going to give us a sort of gross looking situation here, and that's okay. We can just leave it as whatever values it happens to be. So 17 halves squared minus, what was our omega? We had 32 for our omega squared, so 32. And the t, remember, is on the outside of that square root, right? So it is not on the inside. Plus C2 e to that same lambda squared minus omega squared. Right? And so we can say that this is our general solution here, okay? Now, similarly to before, we can also say, hey, let's go ahead and find those constants. All right. Now, I do want to make sure we get to a bunch of the other examples today. So we might not finish this problem, but what I would like to make sure we know is how do we set up the initial conditions for this particular problem? Okay. So if we go back up to the top, and we were trying to unpack the initial conditions, I think that we might find some of the same ones that we used before. In particular, we might notice that the spring is initially displaced 6 inches upward from its equilibrium point. And so we could say for one initial condition that our x of 0, like our initial position, is actually a negative 1/2, right? 1/2 because it's 6 inches and we need it in feet, and negative because we're moving in the opposite direction from gravity. Then we know that there's typically an initial condition based on velocity as well, right? We're looking at position, we're looking at velocity, because all of this is to say we started with this idea of acceleration, right? And so if we look at what we have, again, sort of same as what we had before, given an initial velocity of 1 foot per second downward, that means x prime of 0 is going to be 1. Right. And you can go ahead and use those initial conditions to find your C1 and your C2 coefficient. All right, so use to find C1 and C2 coefficients. All right. All right. So I will say that in general, I tried to stay away from like fairly gross numbers on the homework. So hopefully it'll be a little bit more smooth when you're taking a look at those homework questions. Okay.
Hey, Judy.
Yeah.
Can I just one quick question? I could be wrong here, but the C2 term, should the E be to the negative
Oh,
square
yep.
root?
Yes, you are correct. There we go. Thank you for catching that before I memorialize it on the internet. All right. So yesterday we talked about these different cases, right? And it's so important to kind of come back to like, what is all of this actually looking like? And so we've talked about this overdamped stage where we have these real roots. They are distinct, right? And it happens that these the motion is, it doesn't ever get a chance to be oscillating, right? That spring never really gets a chance to sort of compress and extend, because the solution or whatever medium it's in is so thick that, or whatever damping factor there, it doesn't have to be external, but it could be in the system, right? Any damping factor is so strong that it's basically not really allowing it to move very well. And so the second case we're going to look at is this idea of critically damped, where we're looking at what happens when there's a real repeated root. And when we're looking at this, we're imagining that the damping is there, but it's a little bit less than the overdamped. And in fact, as soon as we move beyond this stage, we're going to get a situation where the motion, the oscillating motion, happens much more easily. Okay. And so kind of keep those visuals in mind as we take a look at this example right here, all right? So a mass weighing 8 pounds stretches the spring 2 feet, assuming that a damping force numerically equal to 2 times the instantaneous velocity acts on the system. Determine the equation of motion. So we're looking for that x of t at the end, if the mass is initially released from the equilibrium position with an upward velocity of 3 feet per second. Right? So what we have here is we actually have quite a few conversions that we need to make. We have some factors that we need to find, like what is our spring constant? What is our 2 lambda, right? How do we use those to put into our equation? And then how do we solve that? Okay. So let's begin with our convert as necessary, right? So a good thing to start with, I see that the mass weighs 8 pounds, but I also know that means that the weight or force is 8 pounds, right? So that I have to convert to the slug, so I can actually use that value as my mass, right? And so from yesterday, we might remember that mass equals the weight over gravity. So we'll get 8 over 32, or we'll get a quarter slug for that mass. And that is the M value that we can use in a lot of these, the following parts, okay? Now, let's see. We notice that the spring, I keep saying string, it's not a string. The spring gets stretched by 2 feet, all right? That's already in feet, so we are good to go. And upon inspection, everything else in here is in feet and seconds, so we're good to go, okay? Now, what we're gonna take a look at is finding that spring constant. All right, so we're going to find our K. That part was familiar. And we're going to find our 2 lambda. Right, so this is the place where we sort of find the values that will help us write that differential equation. And so to find that spring constant, we can say F equals KS. And what do we plug in? Well, we know the weight is 8 pounds, and that stretches the spring 2 feet. And so with a little algebraic manipulation, we can see that our spring constant is going to be 4. Now, similarly, we can actually shortcut our way of finding 2 lambda in this case. So 2 lambda equals beta over m, right? That was an equation that we were given when we first saw the free damped spring motion system, all right? Now we want 2 lambda because that's going to go into our actual differential equation. But our beta, and this is new, this is telling us things in a slightly different way, but this beta is actually when they say that there is a damping force numerically equal to 2 times the instantaneous velocity. What that means is they are telling us your beta equals 2, okay? And our mass, we know because we found that in the very beginning, is 1/4. And so we end up with 2 lambda equals 8. All right, and we're going to be able to grab both of these values and use them to help us write that differential equation. So write, solve the differential equation. All right, now remember, in this differential equation, we already divided by m. All right, we already divided by m. So we've got our d squared x dt squared plus our 2 lambda dx dt plus our k, we called it omega squared, x equals 0. All right. Now, omega squared was just a fancy way of saying k divided by m. And so when we plug in all those numbers, we get 8 dx dt plus, let's see, we get 4 over 1/4. That gives us 16 as our omega squared, right? We had to combine k, and particularly to do k divided by 1/4, and that would give us the 16, right? Now, this is good. If you look at the structure of this differential equation, you might notice that as soon as we write the characteristic equation, we actually have a perfect square. And that is how we know that we're going to have this critically damped situation. Okay, if your characteristic equation, so r squared plus 8r plus 16, is a perfect square, then you have a critically damped system, right? And so we can factor this, r plus 4 squared equals 0, and that will give us r equals -4. Okay, so we found our root. It is indeed repeated and real, right? -4 is a real number, and there's 2 of them, so it happens twice. And so what we're able to do with that is say, let's write, based off of what we know of our real repeated roots, what is a general solution, right? And we know from the previous chapter that we have x of t equals, and if they're repeated, they look so similar, right? C1 e to the r plus RT plus C2, the repeatedness means there's an extra T in there, right? So real, repeated, we're going to use this form. Now we just plug in our -4, right? So X of T is C1 e to the -4t plus C2 t e to the -4t. Now, I've not seen many of your handwritings in terms of the letter T lately, but you'll notice that I put a tail on all of mine because if I just write this, sometimes it becomes a plus sign in my head. So I've sort of over the years taken to writing my T's with a little tail so I can tell the difference between a T and a plus sign. Small potatoes, but whatever helps you, minimize any mistakes. All right, so we've got this differential equation and we've got the general solution. And so our last step here is to really apply these initial conditions and find C1 and C2, okay? Now, I don't think it's the folks who are attending class that are having this problem, but if you happen to be working with anyone in this class who is not attending class, you may want to remind them that you actually have to find values for C1 and C2. Okay, I'm still seeing some folks sort of stop right here and call it a day, but if there are initial conditions, we do need to take that extra step. Okay, so let's go back to the question and see what initial conditions we actually have. All right, so I'll give you a moment to read that. And then if you want to either unmute or type into the chat what you think the, where's my chat box? All right, what you think the initial conditions are for this particular problem, then we can go ahead and apply those and see what we get. All right, so I've got some guesses in the chat, and I would agree. I think when you start to look for those initial conditions, especially if we're looking at a second order differential equation, you really want to think, what do I know about position and what do I know about velocity, right? So the position, it says that it is initially released from the equilibrium position. Equilibrium position means that that position is where we call the center. So we're going to call that 0. Okay. Now, the velocity, though, it is also released with an upward velocity of 3 feet per second. And so this is where we want to be careful because it is 3, but because it is the velocity is propelling it in the direction opposite of gravity, we want to make sure we have that negative in the front there. Okay, so we have a 0, 0 that we're going to plug into the general solution, and then a 0, -3 that we're going to plug into the first derivative of that general solution. All right. So let's go back here and let's say x of 0 equals 0 and c1 e to the 0 plus c2 times 0 times e to the 0. And this is where it's so important that you actually have that extra t in there because that's going to turn the whole last term. All of that's going to 0 out, right? As soon as you multiply by 0, that term is gone. Now, e to the 0, however, does not go away to 0. That goes to 1. And so what we find from this first initial condition is that c sub 1 equals 0. Now we have to find the derivative before we can plug in our second set of initial conditions. So we got a little chain rule. And we got a little product rule. We're just learning U sub in my Calc 1 class. We just did that today, and I think that they were like, you can undo the chain rule. I was like, yeah, you're going to use it a lot. And I think in this class, in DiffyQ, we tend to use the chain rule a lot more than U sub, but the U sub definitely sneaks in there quite a bit. But they have no idea what they're in for. All right, so we're going to go ahead and plug in our second initial condition. So we've got -3 is equal to plugging in a 0 everywhere. And only the term where we multiply by the 0 does that go to 0. Otherwise, this goes to 1, this goes to 1. And we end up with -3 equals -4c1 plus c2. And it is like a system of equations, but we actually already have c1, right? We have c1 as 0. So if we substitute that in, we'll see that c sub 2 equals -3. And so to be thorough, we're going to go back and say my equation of motion, including coefficients, is just going to be -3t e to the -4t. So it's okay for things to zero out as you are finding those coefficients. I think particularly at this level, we're going to see that sometimes they zero out, and that's okay. In higher level classes, I think it's a little bit more situational. Some of them might zero out, but more than anything, in a lot of the upper level classes, you're finding these coefficients, but these coefficients are just like these giant integrals of all of these other things. And then like you just kind of leave it like that and it's okay. All right. So what we're doing here is really setting the stage, especially if you're going to be in applied math and you're going to take more differential equations. Like the skills we're using, the process we're using is going to be the same. You'll just be doing it with much more complicated functions and situations in upper level classes. All right. So let's take a look at example 5. Now, I bet based off of the structure of the notes, we should not be surprised if example number 5 is an underdamped situation, right? But how would we know, like, as we're working through the problem, that it is an underdamped situation? Like, what clue are we sort of waiting for to pop out? Yeah, exactly. Right. So in the chat, David said complex roots. And so if we convert, we find our K and our 2 lambda, we write and solve our differential equation, we get to that characteristic equation. If that characteristic equation has complex roots, then what we're going to be looking at is a situation of underdamped, meaning it is most similar to that simple harmonic motion. It's just that it's going to be oscillating, but it's the waves or the motion's going to get smaller and smaller as you go. Okay. All right. So let's take a look at what we have. What might we need to convert? And we have a mass weighing 16 pounds is attached to a 5-foot long spring. 5-foot long spring is totally fine, but I already know I'm going to have to find the mass, which is the weight divided by gravity. So I'll get 16 over 32. I'll get a half a slug for the mass. Okay. Now, if you're asked to convert units, a lot of times they are nice fractions like 1/2, 2/3, 3/4. Okay, they won't be like outrageous situations. So one good clue is if you're sort of dividing and you get a really weird number, maybe you divide it by the wrong number. Okay. Now, the mass weighing 16 pounds is attached to a spring that is already 5 feet long. Okay, so it's not that you put the spring, the mass on the spring and then it increases the length by 5 feet, right? You have a 5-foot long spring and then you attach the weight. Then after you attach the weight, the spring stretches more. It stretches to 8.2 feet. And so almost in preparation for finding the spring constant, what would we say is the overall displacement of the spring based on that weight?
Just be 3.2 feet, right?
Exactly, exactly. And so like, how did we get that 3.2? Well, we took 8.2 and we subtracted 5, right? That gives us the difference. How long did it grow? It grew 3.2 feet. Okay, and so even though that's not technically converting anything, it might be useful to sort of jot that down in the beginning so that as you move forward, you know what numbers you're plugging in. Okay. Sometimes I even write my initial conditions down here so that I have those ready to go. You can do whatever order feels best for you. I feel like in more complicated problems, it's nice to have your initial conditions right off the bat. But I think at this level, it's really okay either way. All right. All right, so let's find our K. We know by now that K is going to equal force divided by S. And in this case, it'll be the weight. So 16 pounds divided by 3.2 feet. And that actually gives us 5 as our spring constant. Okay. Similarly, we're going to find our 2 lambda. And that is going to be equal to beta over mass. And I know the mass is 1/2, so I'm going to go ahead and put that there. But we need to go back into this problem and we need to find out what the beta is. All right. And so before we do that, let's kind of go back to the previous problem where in the green highlighting, we said that a damping force numerically equal to 2 times the instantaneous velocity acts on the system. And that statement corresponded to beta having a value of 2, right? So a damping force numerically equal to 2 times the instantaneous velocity, that's our beta. So if we go back down to example number 5, right? Example number 5, let's see, the mass is initially released. That looks like an initial condition. Find the displacement. Okay. So now it's almost at the end that the surrounding medium offers a resistance numerically equal to the instantaneous velocity. What that means is our beta in this case is just going to be 1, right? So if we said the surrounding medium offered a resistance 3 times the instantaneous velocity, then our beta would be 3. Or if we said the surrounding medium offers a resistance that is 20 times the instantaneous velocity, then our beta would be 20, okay? And so we want to be real careful here. I know that 1 divided by 1/2 is not 1/2, but sometimes when we move quickly, we sort of lose sight of that, right? So it's 1 times the reciprocal of 1/2, which gives us 2. And now that we have our K and we have our 2 lambda, we can set up our differential equation. And as we go through this, we do want to make sure that that discriminant is going to be negative because that's how we'll know this is an underdamped situation. So right, solve differential equation. And so we're going to say d squared x dt squared plus, let's see, 2 lambda, so 2 dx dt, plus not just k, so not just 5, but 5 divided by 1/2, which will give us 10. Okay. Now the corresponding characteristic equation we'll get is r squared plus 2r plus 10 equals 0. And we can see immediately that this is non-factorable. And so let's go ahead and use that quadratic equation. All right, so negative b plus or minus the square root of b squared minus 4 times a times c. Yep, it is going to be underdamped because I've got a negative underneath that square root over 2. Okay. We do a little bit of mental math. We get negative 2 plus or minus. let's see, 4 minus 40 is negative 36, so 6i over 2. And then I get negative 1 plus or minus 6i. Okay. This one is actually unlike the most recent examples we've seen. A lot of the examples we've seen recently,
Do you divide the 6 also or no?
oh my gosh, yes, that's a 3. I'm so sorry. I feel like the more math I do, the worse my arithmetic gets. It's pretty terrible. Okay, yes, so negative 1 plus or minus 3i. Thank you for catching that. But what is different, other than that I didn't divide correctly, but what is different from some of the complex roots we've seen recently is a lot of our first numbers have been 0, right? And so I just want to bring our attention to the fact that this negative 1 is not a 0. That means we're going to have that e term in there as well, okay? So our general solution with our complex roots should look something like C1 e to the alpha cosine beta t plus C2 e to the alpha sine beta t. And you could use alpha and beta, or we've used lambda and mu before. So whatever helps you distinguish between the real part and the imaginary part, that will allow us to write our general solution. And a lot of times, because both terms contain that exponential one, right? So e to the negative t, if we think about what this looks like, and I think this is pretty cool, but e to the t looks like this, right? It's exponentially growing. However, e to the negative t looks something like this, right? It is decaying. And so this decaying part is what eventually stops the motion of this from just going up and down, up and down, up and down in a perfect world where it never ends. Okay, so this e to the negative t is the part that says, hey, these waves are going to get smaller and smaller and smaller as you go over time. Okay, so because both terms have that, a lot of times we'll actually just factor that out to the front and write it like this. Okay. That is up to you though. You don't have to write it this way, but I think it does make it a little bit easier when you're plugging in initial conditions, because we don't really have to worry about this part really, because that will never go to 0. We get to focus on the inner parts of the solution. Okay. But let's revisit the question and see if we can identify what our initial conditions are. All right, so let's scroll back up to the top. What do we have for our initial conditions? What are your guesses? We know we're going to need a position. We know we're going to need a velocity. All right, so maybe we start with our displacement. What do we know about that displacement? Well, the mass was initially released from a point, from rest at a point 2 feet above the equilibrium position, right? 2 feet above that equilibrium position. If we're staying in line with that idea of, gravity pulls things down, that will be our positive direction, then we would indeed say that x of 0 equals -2. And let's find out about the initial velocity. Okay, now I think this one is a little bit trickier. So I like your guess of x of 0 equal, or x prime of 0 equals 1. But let's read this real carefully here. It says that the mass is initially released from rest. From rest, meaning that we sort of brought this mass up 2 feet above the equilibrium position. We didn't push it and we didn't like throw it down. We just kind of let it go. Okay. And so what that implies is that our initial velocity is actually 0. And that is because we have the released from rest. All right, released from rest. That is the key phrase that tells us x prime of 0 equals 0. Okay. And so if we go back down to our question, we can apply the first initial condition. We can say x of 0 equals -2. And that's going to give us e to the 0. We get c1 cosine of 0 plus c2 sine of 0. This part does start to feel a little repetitive, and that's absolutely okay. All right. In all the differential equations classes I've taken, you sort of get to this point and you're like, oh, okay, now I'm in the home stretch of this problem. We know this is going to go to 0. We know this is going to go to 1. And so we end up that C1 equals -2. Okay. And then we want to take our derivative and see how we can find, apply the second initial condition. And so we can go ahead and say that we're going to use our product rule. And so e to the -t times the product of the inside plus 3c2 cosine 3t plus, now we need to take the derivative of that outside piece, -e to the -t, and then we keep our inside the same. Right? And now we can plug in everywhere that t is 0, my whole expression is going to be 0. So 0 equals e to the 0, 0 plus 3c2 minus e to the 0, c1, and then the c2 term goes to 0. Okay, and so this is actually one of the reasons why I know that it is, if you've never used LaTeX before, it was probably like felt very overwhelming in the beginning of the summer session, right? Because we're in a summer session. There's so much more to learn other than LaTeX. But the nice thing about LaTeX is when you do a problem and you sit and you type all of this out, when you're going to do the next problem, you just copy and paste your code and then you go back in and you change your numbers. And so in that way, there's actually a lot less writing when you're using LaTeX. So just to kind of put a bug in your ear, especially if you are going to take some higher level classes, that you're starting to think about like that programming piece, just making your work look a lot cleaner, but also a lot less writing on your part. Okay. All right, so what do we have? We have 0 equals 3c2 minus plus 2, because C1 is -2. And so we're going to find C2 to be -2/3. And then we're going to put those all back in our equation, and we're going to get x of t equals e to the -t. Let's see, -2 cosine 3t minus 2/3 sine 3t. Okay. And so that, my friends, is a case where we have an underdamped situation, Okay. All right. So I feel like my timing is all off with this class today, but we're going to take a look at one last situation, this driven and forced motion, and then we're going to call it a day. And I think based on last week that I did ask you to sort of learn independently on quite a few things, the extra time, the gift of time, so to speak, can be used to maybe take a look at the discussion that's due tonight, because I asked for some questions like, what is it that you want to see tomorrow, right? Or not tomorrow, but on Thursday. So as we're starting to prepare to review for this exam on Thursday, how can I support you? And the earlier you put your things in the discussion that's due on Wednesday, the easier it is for me to kind of plan for what we might do on Thursday. Okay. All right, so let's take a look at this last situation. All right, so we've got this driven and or forced motion. All right, and so this we might actually think about as our non-homogeneous situation. Right, we notice we have the almost exact same differential equation as we did in the previous part when we had the free motion. But now there's this other function on the other side. So what does that function even mean? Okay, that function, all right, first of all, how did we get that capital F? Well, capital F of t is equal to lowercase f of t divided by the math, right? So we want to make all the leading coefficients 1, so we divide through everything by m. And so f of t, capital F of t, is another way of saying little f of t over m, right? Now this, the very fact that this is non-homogeneous, right? Because we don't have anything equal to 0. Because we have non-homogeneous, what we are doing is we are going to solve by some methods that we learned in chapter 4, okay? And so in particular, we might want to look at the tables, where we sort of guess the type of solution, or we could look at the Wronskian method. Okay, so the Wronskian sort of has that long formula with it. You plug things into it and call it a day. All right, there's a lot of integration in that one, but it does usually work out fairly nicely. Now, in taking a look at the homework, and taking a look at the homework from this week, one thing I noticed was that some people use like the table method for everything, and some people use the Wronskian for everything. And again, I'm not sure that it was necessarily folks who were present right at this moment, but think about the fact that part of the purpose of the homework is to practice the different methods, right? And so if you are looking at a question that you're like, I could solve all of these by a table, but there was this Wronskian thing that I didn't really use yet, maybe try and find that question that you're like, oh, I could use the Wronskian for that one, and just practice that method. Okay, it is very open-ended, because ultimately, as you sort of move higher and higher in the math, it doesn't necessarily matter what method you use, but it's always nice to have more than one method in your back pocket. Okay. And so we're actually not going to be solving this differential equation, but I did want us to just note these important things, like what does capital F mean? Reminder that this is non-homogeneous and that the methods we should choose from are either guessing from the table or the Wronskian method, okay? I think the example that we have here is one where we can guess the solution form from the table, but I know I still owe you a video on the Wronskian, so I've not forgotten about that. And maybe that can definitely be one of the things that we review on Thursday, okay? All right, so we have this question, interpret and solve the initial value problem. And so for this question, we're almost going to go backwards a little bit. I'm giving you the numbers and I want you to tell me what those numbers stand for if you were to write your own word problem, okay? And so we're working backwards here. All of the coefficients are going to be really important to think about, like, how might someone write this in a word problem and disguise it so that I didn't actually know that it was going to be this number, okay? All right, so let's start with this 1/5. All right, now normally we divide through by that 1/5, right? Normally we divide through by the 1/5, but before we divided through, let's kind of compare this to the equation up here. This one right up here, that 1/5 corresponds to the mass, right? And maybe it would be beneficial if I sort of copied this down here so we could put it right below. All right. And so some of the terms have been moved to the left-hand side, but the coefficients there should still be the same, right? The only thing we didn't do is divide through yet. And so this 1/5, we might notice, is actually the mass of whatever we have for our object, okay? So our mass equals 1/5 of a slug. Now, I don't actually know that it's a slug. We've just sort of been working in the imperial unit, so we can kind of just go ahead and put that there. If you didn't put any units, that's okay too. You would just want to make sure that you could sort of justify that all your units sort of match together, okay? Now, I'm wondering what this 1.2 stands for. Based on the equation, can anyone tell me what this 1.2 stands for?
It's beta.
Yeah, that's going to be our beta, right? And it's a plus because it was on the other side and we just added it to the left-hand side, right? So we might say that our beta is 1.2. Maybe another way of saying that is that the damping force is 1.2 times the instantaneous velocity, right? That might be a phrase we can use to give that number. All right, what does the 2 stand for? And as we sort of scan through this other one, we might notice k is 2 is a coefficient for x, which is what k is. So that means that our spring constant in this case is actually 2, okay? Now, last but not least, we have this whole big equation on the other side. All right, and so this corresponds to our f of t, and that just tells us about our driving force, okay? So it is like an active force that is being applied to the system, almost making it move in this, with this relationship, okay? So this is our driving force. And so in this idea of interpret and solve, what you've done here is unpack what each of those numbers means and given yourself an idea of what it might be like if they ask you how to do this in a word problem, like in order, and not just to write the equation, but how do you unpack that information? Now, the last piece I want to talk about is the initial conditions. All right, so how do we interpret these initial conditions? Can someone tell me what phrase I might use to describe x of 0 equals 1/2? Good, yeah. Sorry, continue.
I was just gonna say that it would be the mass was released from 1/2 units below the equilibrium.
Good, good. All right, so initial position is a half a foot, or whatever keeps you in line with the same units. So initial position is a half a foot below the equilibrium point. Good. All right. And then the x prime of 0 equals 0. We just saw that, right? A sneaky way of saying that might be that it is released, right? So we sort of bring this mass a half a foot below the equilibrium point. We don't push it. We don't like push it up or push it down. We just let go. And that is a situation when that initial velocity is going to equal 0. Okay. So if you feel confident interpreting these, that is a good place to be, because I think you get to practice a lot of how would you put those numbers into the actual equation. Okay. And so what we're going to do here, we're going to go ahead and solve this. But before we solve this differential equation, we have to get rid of that 1/5, right? We're actually going to divide everything through by that 1/5. And so by dividing by 1/5, we get d squared x dt squared plus, let's see, 1.2 divided by 0.2 gives us 6, plus 2 divided by 1/5 gives me 10, and 5 divided by 1/5 gives me 25 cosine of 14.
Hey, Judy,
Yeah.
just for simplicity of notation, are you okay if we just use x double prime and x prime instead of writing out the d2x over, or you want it written like that?
I was just thinking that. I feel like I was just thinking that, especially if you're doing LaTeX, if you want to write it like this, that is absolutely fine. I have no preference one way or the other. I think something like this is like when I get lazier, I'm like, I just don't want to write out all those fractions, and that's fine. All right, so either way, whatever you choose, you now have a situation where we're going to solve this non-homogeneous equation, right? So if we rewind our brains to last week, we're going to solve the associated homogeneous equation. Separately, we are going to guess a solution form for the right-hand side. And then at the end, since we have initial conditions, we'll be able to find all of the constants, our C1, C2, and then our A, B, or however many more we have of those on the right-hand side, okay? So now let's go ahead and find our Y sub C. All right, so that is the associated homogeneous equation, and we're going to get m squared plus 6m plus 10. You could use r, either one is fine, equals 0. Let's plug everything in. We're going to get m equals -6 plus or minus 36 minus 4 times 10 is 40 over 2. Ooh, looks like we're going to have a underdamped situation, right? Because 36 minus 40 is going to give me a negative in there. So let's make sure I do this right. -6 plus or minus 2i over 2. I'm going to divide everything by 2, so -3 plus or minus I. Okay. Now again, this -3, that is the real part, that's going to give us that damping factor on the outside, the e to the -3t, the decay function that makes the motion stop eventually. Okay. And so this is going to give us y sub c equals e to the -3t times c1 cosine of t plus c2 sine of t. All right, now that's half the battle. We've done the homogeneous part. All right, so when you get to the exam next week and you're like, oh, she's only looking for a homogeneous equation solution, you should be like, thank goodness, right? Because you only have to do that side. The more complicated part comes in when we have the non-homogeneous situation, meaning we have that function on the other side, that driving force or whatever the scenario is. And so let's go ahead and we'll just continue right on the other page. Find y sub p, all right? And let's go ahead and guess a situation. So anytime I see a cosine, I'm thinking y sub p equals a cosine 4t plus b sine 4t, all right? And so let's be thorough. Let's find our y prime, our y double prime, so we can substitute those all into our equation and figure out what our a, b, and c are. All right. Now, I did see a few folks who just were like, here's my y sub p, and then they just added that to the y sub c. You got to find your numbers for a and b. Okay, so in case I didn't make that clear earlier, when we write our final answer, we should have a number for a, and we should have a number for b. Okay, and because we have initial conditions, we're also going to have a number for C1 and C2. All right, so let's use that chain rule. Let's use the chain rule again. All right, now what in the world are we plugging that into? Well, I guess I should have used y, but y double prime plus 6y prime plus 10y. We're going to plug in all of those. Second derivative where there's a second derivative, first derivative where there's a first derivative, regular guess where there's a regular guess, and it should equal 25 cosine of 4t. So double prime plus 6 single prime plus 10.
Judy, I have a question about the notation.
Of course, what's up?
So you're writing it as a function of y, but it's like as a function of x. Would you still write y sub p, or would you write x sub p?
No, we should be thorough here. Let me change these y's to x's.
Does that question make sense?
It does. It makes 100% sense.
Cool. Just making
So
sure.
yeah, because I
Okay.
think when we were
Okay.
solving them before, they were all y equations, right? So we had y sub c and y sub p. But since we are now in x, because we use x for position, we should be accurate and write x's here instead of y's.
Okay, cool. Thank you.
Thank you. All right. So we plug that all in. We hope that equals 25 cosine 4t. All right. Is there anyone who's feeling like, anyone with us right now who's feeling like they're not really sure how to go through and like set up the system of equations? because that would be an important thing to make sure we understand. And I know that I don't always do this part, so I'm happy to walk through one if you feel the need to. Otherwise, I can just tell you what your A and B are equal to. And you can just send me a direct message if you don't want to say it out loud. That is absolutely fine. Okay. All right. So I've noticed that some folks are setting up matrices, and that's great. Some people are color coding and underlining so that they're combining their like terms. Whatever method works for you is absolutely fine. But I believe at the end, we should get -25 over 102 for A. And B is going to be 100 over 102. All right. And so what does that mean? That means that my x sub p, thank you for the notation correction, x sub p is going to be -25 over 102 cosine of 4t plus 100 over 102 sine of 4t. Right? Now, some people might be wondering, like, why didn't I reduce the 100 over 102? Because that definitely reduces. Sometimes we just pull out that 102 or like whatever that common denominator is, just so we don't have fractions inside. We sort of bring that common denominator to the outside. But it's really up to you how you choose to write that. But what that gives us, x is going to equal, I'm going to go ahead and grab this solution. Right, so that's part of it, plus this as the other part to the solution, right? So we have the first part, which is our x sub c, the second part, which is our x sub p, and then the only thing we have left to do is to find our C1 and our C2, okay? And so in order to find that C1 and C2, we're going to go ahead, use those initial conditions that they already gave us, right? We're going to use those initial conditions. And for simplicity's sake, I'll say applying initial conditions gives C1 equals 38 over 51 and C2 equals -86 over 51. And again, whether things are reducible or not, if you have that common denominator, then you can sort of pull that out to the front. And some people just visually like to write it that way better. I don't really care which one you do, as long as your numbers sort of match up. And so we would write a final answer, something like this, if you wanted to pull out that denominator. Whew. That was a very long problem, right? Very long problem that sort of encompasses so many of the things that we learned, because we had a chance to look at sort of the homogeneous solutions, the non-homogeneous solution method, finding those coefficients like A and B, and then applying initial conditions to find our C1 and our C2, okay? I imagine that next week's exam will not consist of like all these kinds of problems, because it would probably take you a solid, chunk of time to work through just one of these, right? So as you're thinking about studying, consider, how long the problems are, excuse me, how long the problems are and what might be realistic in the time frame of an exam. Okay. So I think that is it for today. I'm going to go ahead and stop this recording.